Hi everyone. Today we are going to talk about design for fatigue strength. So before discussing about the fatigue strength, we should have very clear idea about what is a design. So generally when we talk about the design, ultimately it is about a design of any machine element. As we know that when we talk about designing of any machine element, it is not possible to make or design everything as a single component. So for that usually what we will do, we will take any machine means we will divide that machine into so many components and part by part we will be designing. Say for example, this is part 1, this is part 2 and this is part 3, like that. We will be designing all the available parts including the small bolt and nuts we will be designing and later we will be assembling. So these things we have already studied in the module 1. Now coming to this fatigue strength. When we design any machine parts or any entire machine, what is a very important thing to be noted here is the internal loads and the external loads which is acting upon that one. Because when we solve or when we design something theoretically, there may be so many positive things we may get, but practical cases we cannot achieve everything whatever we have done theoretically. So for that we will be considering so many external factors. The very important external factors what to be considered here is the fatigue strength. So now we come to the concept of fatigue. So what is fatigue? How can we define fatigue? So fatigue is nothing but the tiredness which is achieved by any body. So tiredness means how can we explain what is meant by tiredness means. Say for example, let me consider a small metal body which has an ultimate strength of some 100 Newton per mm square. So as we know that when any external load is acting on this particular component, usually the failure will happen when the load is surpassing this yield strength. But in case of the fatigue, before it achieves its 100 Newton per mm square, the material will go under the failure. How means because of the tiredness. For example, consider a shaft which has a circular cross section. Let me name it as the upper part as A and lower part as B. So usually when the shaft is under torque, that is when the shaft is under rotation, usually under top part, that is when I am talking about the point A, it will have the compressive force and the point B will have the tensile force. Similarly, what happens, the points on the A and B will keep on changing stresses. For example, initially what it has on the compression at point A, when it comes to the downside, it becomes the tensile. So similarly, when the same point which is going under repeated compressive and the tensile means what happens, it lands up with the tiredness of the body. So usually because of this tiredness, what will happen, say for example, the material is having the yield strength of 100 Newton per mm square. Because of the tiredness, the material would able to fail before when the material reaches the yield point of 80 Newton per mm square. So usually when we talk about these kind of stresses, that is the repeated cycle stresses happening, we have four different cases. What are the four different cases? Fluctuating stresses, repeated stresses, alternating stresses and the reverse stresses. The example what I have explained here is the reverse stresses. On what basis I am comparing these four different types of stresses is, in this sketch we can able to clearly understand. Look at the first sketch. This first graph is for the fluctuating stresses. Whenever I talk about the fluctuating stresses, I am not considering the rotation or the stresses what is induced on the body along the axis. You can able to see here, this particular line is in the axial part. But whatever the fluctuations is experienced in your body, which is above than the axis, you can able to see here, whenever I am talking about the fluctuating stresses, the important point to be noted here is, always the maximum stress will be more than the minimum stress, since we will be measuring from the axis. Coming to the next one, the repeated stresses. The very interesting point to be noted in the repeated stresses is, here we will be measuring everything with respect to the axis only. When I am talking about the repeated stresses, very important thing is, here always a maximum stress only will be in this, there will not be any minimum stress. Correctly speaking, the minimum stress value will be always equal to 0. So whenever any applications where I will be designing for the repeated stresses, there I can directly say that the minimum stress value is always 0. Coming to the next case, alternative stresses. This is something like very similar to the fluctuating stresses, but what is the major difference here is, in case of the alternative stresses, with respect to the axis only, all the fluctuations will happen. But very important point here to be noted is, always the maximum stress will be greater than the minimum stress. You can see the values what I have shown on the amplitudes. I have considered the first cycle, that is the upper amplitude and lower amplitude I have considered here. In this, the maximum value is measured as 10 and the minimum value is measured as 7. So whenever any cases where I will be talking about the alternative stresses, there it is so clear that always the maximum stress value will be greater than the minimum stress. Coming to the last one, the reverse stresses, the very common type of stresses which can see in almost all kind of applications. Here it is so clear that always the axis will be lying on the reference point only, and always the maximum stress and the minimum stress will be equal to same. And this is the comparison between the fluctuating stresses and the reverse stresses is the only difference. In case of the fluctuating stresses, the reference line will not be the axis line, but in case of the reverse stresses, the reference line will be the axis. Continuation of this one, next will be the SN curve. For the explanation of the SN curve, I will be taking an example for the reverse stresses. So how practically I can come to know that how better I can understand the engineering materials. I have considered any one particular material, and for that I have done some experimental setup. What is the experimental setup I have done? Before that only we have studied what is the meaning of the reverse stresses. Reverse stresses is nothing but where a type of stresses which lies exactly on the axis. So here I have taken a shaft which has a circular cross section, as usually I have mentioned, a point A and point B. As we know that each point will keep on varying compressive and the tensile stresses. So what kind of setup I have done here is, this shaft what I have taken for my experiment purpose, I have connected with an electric motor. By using this electric motor only, I will be applying torque on this particular shaft so that the shaft will rotate. And another side, I have here one more important accessory called the revolution counter. What is the purpose of this revolution counter is, it could able to measure the shaft what I have taken at a different speed and how many cycles have completed, for to measure that only revolution counter has taken. Next, for the experimental purpose, what I have done means, I have done a simply supported beam setup. It means like both the ends of the shaft I have connected with a weight W, so that it acts as a simply supported beam. Now what happens? Coming to the point, I will be applying a torque with the help of an electric motor, so that the shaft will start rotate, and revolution counter it continuously measures how many cycles have been completed. Here the word cycle means that one particular, for example I am talking about the point A, means you should get a complete cycle. Again A should come to B, again B should come to point A. That is the meaning of one cycle. After the experimental analysis, what is the conclusion I will be doing? Whatever from the revolution counter, whatever the data I will be getting here, everything I will be plotting in a semi-logarithmic sheet. Why I will be going with the semi-logarithmic sheet is very important. These kind of experimental analysis can be shown or can be plotted only by using a semi-logarithmic sheet. In the semi-logarithmic sheet, the x-axis I have plotted the number of cycles which is shown here, and the right hand side, y-axis I have taken as an endurance stress. So what is the meaning of the endurance stress? The maximum stress which is produced in the reverse tricycle will be called as the endurance limit. From my experimental setup, what I will be getting? The so-and-so material, what I have done, it may be X material. Well, from the revolution counter, when the number of cycles is 1000, it is getting a low cycle fatigue. It means like any material which could able to rotate till 10 power 3 without any damage means it belongs to low cycle fatigue category. Similarly, I am not stopping the shaft, I will be continuing my rotation, and it will keep, revolution counter will keep on measuring what is the total number of the cycles. When it is keep on increasing, you could able to see here till 10 power 6 the material could able to rotate continuously, means what happens means without any damage it reaches a very important point called the high cycle fatigue. So what is the purpose of this logarithmic graph is, it is so clear that in any application when I am taking for the operation, if it could able to rotate without any damages or without any problems or vibration, whatever thing, till 10 power 3 means, then I can recommend it for a safest design part. With the same material, if it able to rotate till 10 power 6 cycle, then it can be called as the high cycle fatigue. It means like I can refer always a material which could easily cross 10 power 6 cycles without any damage, means that can be always recommended for the infinite life. So whatever the applications where we see that there, if it is mentioned that the shaft is mentioned as the infinite life, means easily it could surpass the number of cycles as 10 power 6. Coming to the next very important concept, strength under fluctuating stresses. So for this purpose, I will be taking the very first cycle, that is the fluctuating stresses. Fluctuating stresses is almost similar to the reverse stress cycle. The only difference is here the reference and the origin point will be not same. In case of the fluctuating stresses, always either the maximum stress and minimum stress, everything will be happen above the reference line, that is the above the axis point. Look at this one. So in this I will be taking only the experimental details what I have done here. First, we will try to understand what is shown in the graph. You can able to see here in this graph I have taken a two part. The right hand side always have taken a tensile and left hand side always have taken a compression. As we know that the failure of this kind of fatigue stresses will happen more due to the tensile part only. So, and in this what I have taken here is, I have taken mean stress as the x-axis and the amplitude stress as the y-axis. And what is the limit for this amplitude stresses? I have taken here as the endurance point as the limit for this amplitude stress. Coming to this one, this first line. So what I will be doing means, initially I will be plotting a line from the endurance limit to the yield point. When I am talking about the yield point, it is so clear that I am talking about the ductile material, because ductile materials only will be having a yield point. Coming to the next point, what I have chosen is the ultimate point. It is so clear that here I am talking about the engineering materials of the brittle characteristics. And here one more curve, a parabolic curve we can able to see here. And very important thing what we can able to see here is this scattered points. What does the scattered point means? These are the different points where this kind of experimentation has done in the fluctuating stress category, in the stress conditions, where for the different materials, different failure points have measured here. So from this graph, so what exactly we are learning is, for example, in the scattered point mean, it is mentioned as so and so different material with different composition. This scattered point is nothing but so and so different material with the different characteristics and the different properties. So whenever I do any design for any component, I can directly go with this particular graph. For example, stainless steel is the material I am looking for any design of any one particular part. I need not to worry about the properties of the particular material. Looking at this graph, I can able to find out till which limit or till which task the material could able to perform. Now coming to this one, the point which connects from the endurance limit to the yield point, the scattered points I have connected as a straight line. That is called as the Soderberg failure lines. What is the meaning is, any material if could able to withstand within this limit means we can recommend that material for the safer design. In case if it is crossing this particular line means we can call it as the unsafe material for so and so design. Coming to next one, and just now I said Soderberg failure line is for the tensile materials, that is called the ductile materials. Coming to next one, this one, that is the Goodman's failure line. Goodman's failure line, it is always for brittle materials. So whenever any brittle material, for example cast iron, so you will be very confused because there are so many materials which could able to give the same thing, same like the properties which I am looking for any particular design. So cast iron is a material, even similar materials will be there. This scatter point show that different material properties. So when I am talking about this Goodman's thing, without any like a confusion, I can directly go with any particular point. Again, the same case it is applicable here. What is the same case here applicable is, in case any material characteristics if it is crossing this particular line means we cannot recommend that particular material for any of the design purpose. Coming to the next one, Gerber parabolic curve. This is very very important, and practically it is not used for any of the design cases, because this Gerber parabolic curve usually will be recommended for the non-metals. Non-metals means either it can be it doesn't belong to the ductile category or the brittle category. Examples I can say like the ceramics, the fibers and all those things. And here also whatever the material which is invented in the engineering category, that also taken for the different experimental analysis for the different stress cases, and everything is plotted here. This is very rare cases, and for the common engineering application usually Gerber parabolic curve is not recommended. So why we are going with these kind of materials and all other things means, whatever design we do for any particular machine or any particular part, usually we will land up with inadequate situations. It means what? The details, whatever we gather for the proper design is insufficient always, because there will be so many environmental factors, there will be so many material properties, so many material factors will be that directly affect the performance of the life of this one. So this is again a part of any particular design. that is the fatigue strength. So in case if any material for any particular design which can go under these kind of stresses category, then I will be definitely referring this SN curve under this fluctuating stress curve. Similarly, the strength under fluctuating stress, the graph what I have shown here, even the same curve can be shown for all the different cases, so that we could able to pick up what is the best material which is suit for my proper design.